Hello, and welcome back to Greg Does Physics. My name is Greg, and we are going to be doing some physics today. So, for this episode, I'm actually going to be doing two problems. The first one is 1.16, and the second one is going to be 1.39. The reason that I'm going to be doing these two problems together is because, well, before I get into that, let me just say that while I do like Griffiths' textbook, pedagogically, I think it's a great introduction to E&M, I do have a problem with it in some cases, and this is going to be one of those cases. In that, when he gives you problem 1.16, if you're working through the book and do 1.16 with only the information he's given you prior to that problem, and you solve out this problem, you're going to get the wrong answer. And Griffiths doesn't explain that immediately. He doesn't explain it in the problem text. He doesn't explain it in the section later. And in fact, it's actually more toward the end of chapter 1. I believe it was section 5? Section 5, the Dirac delta function, where he finally explains this discrepancy and where it's coming from. And so for that reason, I'm going to start with 1.16. I'm going to then do 1.39, which is where you first become fully aware of the discrepancy at hand, and then I'll explain it a little bit afterward. But if after I've gone through this problem you still don't understand it or you want to hear more about it, I highly recommend that you read section 5 on the Dirac delta function, because that will go into more depth explaining this problem and where it comes from. Anyway, let's get to the problem, shall we? So 1.16 asks, sketch the vector function v equals r hat over r squared and compute its divergence. The answer may surprise you. Can you explain it? So I've already sketched the vector function here. It's, nothing crazy. It's a vector function that points radially outward everywhere, hence r hat. And the length of those vectors decrease the farther out in r you get, with an inverse square relationship. Now, divergence, a way to think of divergence is that it's sort of a measure of how much from a certain point in space the vectors are diverging away from that point. And if ever you have seen a function that you would think to have a high positive divergence, I would think this would be one of them, because at every point the vectors are diverging outward, fully outward in the r hat direction. So before we compute this, you could look at that picture and expect there to be a high positive divergence. Is that what we get? Well, let's calculate this and see. So r hat is the same thing as the r vector, the position vector, over the magnitude. So we could also write that like this. And then this would be x hat plus y hat plus z hat. This is just the position vector in Cartesian coordinates. You could do this in spherical coordinates, and in fact that's what I will do in 1.39. The reason I'm computing in Cartesian coordinates right now is that even though it's a bit more not as easy to deal with, still not hard, but certainly not the way I would recommend computing this. The reason I'm doing it with Cartesian right now is simply because at this point, with 1.16, Griffiths has not introduced spherical coordinates yet. So if you were going along with the book in order, you would compute this in Cartesian coordinates at first. And then this would be x squared plus y squared plus z squared. Magnitude, this would be the square of the magnitude of the position vector, except it is cubed, so it is 3/2. And so then the divergence, as you should know, is the dot product of the del operator with the vector function that you are computing, for which you are computing the divergence. And so in Cartesian coordinates, the del operator would be x hat ddx plus y hat ddy plus z hat d z. The reason I'm writing the hats on this side is just so it doesn't look like we're differentiating the direction vectors, unit vectors. So with this in mind for del and this equation for v, why don't we compute the divergence? So I'll start by just computing it in the x, so the multiplication of the two x hat components. So it would be ddx differentiating x over x squared plus y squared plus z squared to the 3/2. So you should know quotient rule. That's what we're going to be using. So let's quotient rule this out. The first term, of course, x is going to be differentiated to 1, so then we just get x squared, this bottom term, in the denominator, x squared plus y squared plus z squared, 3/2, minus x times this term differentiated, which would be multiplied by 3/2, the whole quantity is just chain rule, drops down to 1/2, and then times the derivative of what's inside. We're differentiating with respect to x, so it would just be 2x, and then this is all over a denominator of just this squared, so x squared plus y squared plus z squared cubed. Alright, so these cancel out, and so we can see that the, let's sort of draw a bubble around our del operator here. We can see that this then becomes, just to make this a little more compact, I'm going to translate these x squares plus y squares plus z squares back into this r notation, just to save a little space. Of course, this quantity x squared plus y squared plus z squared is just the magnitude of the position vector squared, or, in other words, r squared. So this would be r cubed minus 3x squared. Oh, is that right? Yeah, 3x squared times r. And this is all over r squared cubed, r to the 6. Okay, so that's our x term. Now, just logically, we can look at how the x components compare with the y components and the z components, and we can see that if we're dotting, for example, if we were looking at the multiplication of the two y components, it would look like this, except it'd be dy, and then it'd be y up here in the numerator. And so we would still get the same denominator, we would still get the same term because we'd be differentiating y. The only difference would be this term over here. Because, again, we would have y instead of x here. This part would look the same since we'd still be differentiating the same denominator, except then when we differentiate the inside of this with chain rule, then we'd be getting 2y instead of 2x. And so if we were going to look at the divergence of v and add everything up, well, it would all be over r to the 6, since everything's over r to the 6. we would get 3 terms from each component, x, y, and z, of this r cubed. So it would be 3r cubed. And then we can bring out this minus 3r, since the minus 3r is going to be the same. And then what's different is that for x we'll have this x squared term, y will have the y squared, and z will have the z squared. So x squared plus y squared plus z squared. Except look at this, this is just r squared. So then we have 3r cubed minus 3r times r squared. But that's just 3r cubed minus 3r cubed, which of course is going to be 0. So it's the 0 vector. So we've computed our divergence of r hat over r squared, and even though, if you remember from the diagram, we would think that it would have a high positive divergence because this equation for this vector function is just always pointing radially outward from the origin. Even though we think it would have that high positive divergence, instead we're getting the 0 vector for it. So that might be your first inkling that something's up, and that is why Griffiths in the problem statement says the answer may surprise you. Can you explain it? And I will explain it in a little bit, but before I go into the full explanation, we're going to now transition to problem 1.39, because that will bring us back to computing this divergence, and once we compute this divergence again, we'll also use it in tandem with Green's theorem, or the divergence theorem as it's also known, and that will flesh out this inkling that we have that something is up here, and then, like I said, I'll explain. So 1.39. 1.39 is a 2-part question. I'll still do part A though. It says, check the divergence theorem for the vector function v1 equals r squared r hat, using as your volume the sphere of radius r centered at the origin. Okay. I'm going to take a little break real quick, and when we get back, I will have this problem written out. Okay, and we are back. So for problem 1.39, part A asks us to check the divergence theorem for the function v1 equals r squared r hat, using as your volume the sphere of radius r centered at the origin, or ball. So we're going to need a couple things. First is that unlike problem 1.16, at which point Griffiths had not given us, if you were going along doing the questions in order as you went through the book, Griffiths had not introduced spherical coordinates at that point. By this point, though, he has, and that'll make our life a whole lot easier, and it'll also give us a chance to compute the divergence in non-Cartesian coordinates and spherical coordinates and see how we do that. So that's good. It's also going to give us a chance to use and test Green's theorem, or divergence theorem as it's also known. That's given by this equation here. The volume integral for the divergence of a vector integrated over some volume is equal to the closed loop integral over a surface for the dot product of that vector and the area of that encloses that volume. Basically what this is saying is that if you were to fill some volume with, for example, a bunch of faucets pouring out water, and this volume, the fluid was incompressible, then the amount of fluid that is diverging within that volume has to be equal to the amount of fluid that is going out through the surface. That's called the flux, and that's kind of a very sort of simple way of explaining what that is. if you don't fully understand Green's theorem, I highly recommend that you read the section on it in Griffiths' textbook. I think pedagogically he does do a great job of explaining it and the meaning behind it, though he doesn't give a formal proof of how it's derived, but for the purposes of just being introduced to it, I think he does do a great job. So the other thing that we're going to need to compute this divergence is the equation for divergence in spherical coordinates. And again, that is given to us by this whole thing up here. And then once we get that divergence, we're going to plug it back into Green's theorem and test that. And the volume we're going to be using is, like we said, this ball centered at the origin with radius r. So let's go ahead and compute this divergence. We can see that the only component of this vector is in the r hat direction. There's nothing in the theta hat or the phi hat, so for all intents and purposes we can just ignore these terms because they'll of course zero out. So then what we get is that this divergence is equal to 1 over r squared ddr times r squared times r squared, r to the 4th, which equals 4r cubed over r squared, cancels, equals 4r. So there's our divergence. Now let's plug it into Green's theorem and see if this works out. So we have 4r, and our volume element in spherical coordinates, this d tau, will be r squared sine theta dr d theta d phi. Alright, so then we can take the 4 out since it's constant. We can have one integral for the radius. We're integrating from r equals 0 to r equals capital R, the radius of the ball, and that'll be r cubed dr. Then we have 0 to pi sine theta d phi. The polar angle, of course, ranges from 0 to pi. And then, taking a little space here, 0 to 2 pi d phi, since the azimuthal angle goes all the way around 2 pi. Alright, so then this equals 4. That's, of course, going to be 1 to the 4th, capital R to the 4th, because then the other term is just 0, so we get rid of that, times 2 for this. I could go out and do that. It's minus cosine theta from 0 to pi, and so cosine of theta at pi is -1, so that's 1, and then at 0, of course, it's 1. You're subtracting it, so it's 1 plus 1. That, of course, becomes 2. And then, of course, that is just 2 pi. You'll find that throughout E&M, you're going to run into problems pretty often that have nothing in the theta or phi. And so you'll see this sine theta, d theta, d phi, these integrals a lot. It pays to just remember that this equals 4 pi, because it makes it just much quicker, because like I said, you'll be seeing that a lot. Anyway, so these cancel out, and what we're left with is 4 pi r to the 4th. Okay, now our job is to compute this integral and make sure that whatever this integral is equal to our 4 pi r cubed. So, v, of course, is our r squared r hat. and it is dotted with this element of area on the spherical shell. It would look like that. It's a little element of area on the shell of the sphere. And you might be wondering what that is. Well, it would just be, since there's no deviation in the r hat direction, you would be looking at you could say d l theta d l phi to get this area. These are not the same as just d theta d phi, because d theta d phi aren't in units of length. They're changes in angles, but not changes in length. And based geometrically, you can do the math yourself, or you can look at in Griffiths and see how he derives it. But the important thing all you really have to remember is that for a spherical shell, what we're going to end up with is that this element of area is going to look a lot like our volume element, because it is going to be r squared sine theta d phi pointing radially outward. That is in the r hat direction. Since these two are dotted, then what we'll get is this closed loop integral r to the fourth sine theta d phi. But we're taking this at the surface of the shell. So r is not a variable here, it's going to be constant. It's going to be constant because it's the radius at the radius of the sphere. So we can actually pull that out and get r to the fourth, capital R to the fourth, and then again this closed loop integral of sine theta d phi. But the limits of integration of this are going to be the same as the limits of integration here, because you're integrating over the entire sphere. The polar angle theta runs from 0 to pi. The azimuthal angle runs from 0 to 2 pi. And so again, I won't write it out because we've already done it here. This is going to be 4 pi. And thus, what we get is 4 pi r to the fourth. 4 pi r to the fourth, 4 pi r to the fourth, they're the same. We have confirmed that Green's theorem works here. So we're confident in our calculation of the divergence, and we're confident that this looks good because Green's theorem has held up. All right, so that is great. That is great. Let's go through now and do part B, because in part B, an old friend of ours is going to knock on our door, and we'll have to beckon them in. And see whether they've changed since we last met them. Because we'll be able to see them now through a new light. And that light is spherical coordinates. Because part B says do the same for V2 equals 1 over r squared r hat. If the answer surprises you, look back at problem 16. Okay. Look back at problem 16, it says. Well, we've already done problem 16, so why don't we see if doing this in spherical coordinates gives us the same answer that we got in problem 1.16. Before we got 0 for the divergence, let's see if we get that same divergence again. And this time, since we have spherical coordinates, it'll go much quicker. Again, there's only something in the r hat direction, so we'll only look at that at this first term. And it's r squared over r squared, so that'll cancel out to 1. This is a constant, differentiating a constant, of course, is going to go to 0. So the divergence is 0. Okay, and if the divergence is 0, that makes this volume equation much easier because it's just 0. So, now our job is to check. Does this corresponding equation equal 0? Does it? Does it? I'm going to get another piece of chalk real quick. New chalk required. Let's go. So, let's calculate this integral. So, we're going to have the same dA, and so we're going to have 1r squared r hat dotted with r squared sine theta d theta d phi in the r hat direction. We can see that these r terms cancel, and this is going to be dotted, so we get sine theta d phi integrated over the boundaries of this spherical shell, the boundaries of this ball. But this is the same integral we've done twice already. What was it? It was, of course, 4 pi. Now that's strange, isn't it? Because Green's theorem does not seem to be holding up here. We got 0 on one side of the equation, and we got 4 pi on the other hand, and those are definitely not equal. If they are equal, I gotta reevaluate what I know about math. But they are not equal, and that seems to be strange because we've been told that this divergence theorem holds up. We weren't told that there are exceptions to the divergence theorem, and yet there seems to be. Now let's think about where this could have gone wrong. Why might this discrepancy be happening? Well, let's look back to our equation here. It's r hat over r squared. It's vectors pointing radially outward that decrease along with the inverse square relationship as they get farther and farther outward radially. But what if r equals 0? If r were to equal 0, we would have 0 in the denominator, and that vector would blow up. So, it seems that we have unwittingly taken along in our calculations something that has blown up at the origin. And that seems to be what might be causing this discrepancy. So, what we in fact realize is that, and what Griffiths will say if you read on in the textbook, is that divergence theorem, Green's theorem, is not wrong. It's not wrong. In fact, what we did wrong is this. This is wrong. The divergence is not 0. Even though you've now calculated it twice in 2 different coordinate systems, it is not 0. It is not 0. And the reason is that we can believe that the divergence everywhere else than the origin is 0. Sure, but at the origin, the divergence is not 0. And this is when something called the Dirac delta function comes into play. Now, I won't turn this into a whole lecture on the Dirac delta function because this is supposed to just be going through problems. But I'll give a quick, just brief explanation. You can imagine the Dirac delta function in one dimension is something that's peaked really, really high in one place and 0 everywhere else. And if you were to integrate this function over all space, you'd get 1. You would get 1. And so this Dirac delta function, you should be familiar with it because it comes up often in physics, and not just in E&M. It comes up in all kinds of different areas of physics, quantum mechanics, for example. You'll use the Dirac delta function. You'll use this Dirac delta function a lot, and it pays to get used to what this Dirac delta function is. You can think of it, you should always be looking at the Dirac delta function as an integrand, as something with which to integrate. Not as its own rational function, because the whole thing is that it blows up at the origin, and it's 0 everywhere else, but you integrate it and you get a nice, beautiful 1. And the Dirac delta function is what we're going to use to resolve this discrepancy in Green's theorem, because we are going to say that the divergence of V does not equal 0. What we're going to say is that it equals 4 pi times, this is the 3-dimensional Dirac delta function. It's basically the same as this, except that peak is at the origin of a 3-dimensional space. And if you integrate it over all of 3D space, then again, you will get 1. And that way, if we look back at our at this first problem here, this divergence d tau, then we can see that if we integrate this over all space, 4 pi delta 3 dx dy dz, that way, and regardless of our coordinate system, this will integrate to 1. As long as we include the origin here, this will be integrated as 1, and thus we'll get 4 pi, which would equal this. All we have to do is make sure that our region includes the origin, because there are going to be no contributions coming from elsewhere. And so I think that's where I'm going to leave it. I hope this has explained a bit better where this discrepancy might be coming from and how we're going to solve it. It tells us that, as we suspected, this is not a divergenceless function, or divergenceless function. Well, it's not 0 everywhere. It does have a divergence, and that divergence is given using this Dirac delta function. That way Green's theorem holds up, and it is just not correct to compute the divergence directly using Cartesian or spherical coordinates, because you are wrapping up into it that which blows up at to infinity at the origin, from this r hat over r squared. There's a problem later in the textbook, which I'll also be doing for a future episode. I believe it is problem 1.63, or 1.64 maybe. I think it's one of those two. And in that problem, we'll revisit this. We'll revisit not this exact problem, but we will compute the divergence for a generalized case of this r to the nth power in the r hat direction, and we'll test Green's theorem. We'll test Stokes' theorem as well with that, and see how the curl and divergence change with n. And that will let us revisit this interesting case of r hat over r squared, where the divergence is not 0. It uses the Dirac delta function. And you might be thinking, it's kind of weird for the textbook, chapter 1, to spend so much time on this specific case of r hat over r squared. It might be strange for me to now, who knows how long I've been doing this episode for, maybe half an hour, to spend this much time just explaining the Dirac delta function and the divergence of r hat over r squared. But it is good to know, because it is going to come up time and time again as you study E and M. And so it's good to know why the Dirac delta function is there, why the divergence is wrong if you just correct it, compute it directly and get 0, and how we use the Dirac delta function to rescue Green's theorem. I think that's all. So if you made it this far, thank you for watching.